कैमरा
Sequin in the night sky. As the stars shine, they tell a million stories, some of yours and a few of mine. Sparkling gems adorn the sky, and you wish to be like them. A dazzling splendor to beautify, and a long road to exemption. As you look upon at night, you feel the wind so calm, assuming a tomorrow so bright, you embellish the innermost charm. As the night enchants its beauty and makes us feel beautiful, it side by side performs her duty by making our every night hopeful. Good morning, ladies and gentlemen. Welcome to the highly anticipated second international conference on advances in nanomaterials and devices for energy and environment, CANDEE 2023, where brilliant minds from around the world gather to exchange ideas, inspire each other, and shape the future. We are Anmol Agrawal and Anjali Singhal, pre-final year students of MBA. We are honored to have all of you join us today as we embark on this incredible journey of knowledge, innovation, and collaboration. This conference serves as a platform for experts, researchers, and professionals to discuss breakthrough, share experiences, and foster meaningful connections. Before we proceed further, let us take a moment to express our deepest gratitude to all the organizers, volunteers, and contributors who have made this event possible. Their dedication and hard work are commendable, and we are truly grateful for their unwavering support. Now, without further ado, let us begin this international conference where minds will meet, ideas will collide, and solutions will be born. To inaugurate this remarkable event, we would like to invite our esteemed guest to the stage for lighting of the lamp and Saraswati Vandana. I would request Dr. Anurag Srivastav, Sir, Dean of Alumni and External Relations, the convener of CANDEE 2023, to guide our esteemed guest on the stage. Dr. Ajay Kumar, Head of Engineering Science Department, our guest of honor, Professor Srinivas Singh, Director, Sir, of ABB Triple ITM, Professor Ravindra Pandey, Sir, Michigan Tech University, USA, Dr. MVG Padmavati, Ma'am, Associate Director, SSPL Delhi, Professor Pankaj Srivastav, Sir, Dean of Academic Affairs, ABB Triple ITM, Professor S.L. Chaprot, Sir.
या कुन्देन्दु तुषारहार धवला या शुभ्रवस्त्रान्विता या वीणां वरदण्डमण्डितकरा या श्वेत पद्मासना या ब्रह्माच्युत शङ्कर प्रकृतिभिः देवैः सह पूजिता सा मां पातु सरस्वती भगवती निःशेषजाड्यापः।
Thank you for gracing us with your presence. We are privileged to have such distinguished personalities among us, who have significantly contributed to the respective fields and continue to inspire countless individuals worldwide. Ladies and gentlemen, we would like to invite Dr. Anurag Srivastav sir, Dean of Alumni and External Relations, to please come upon the dais and address the guest of honor and brief all of us about the conference.
Very good morning, one and all present here in this hall, dignitaries on the dais and off the dais, especially the people on the dais, uh, my motivator, my guide, Professor Ravi Pandey, Professor Chaplet, another my guru who's sitting here, friend of my own guru, Professor R.K. Singh. I remember him today. The motivator and inspiring person in this institute for me, Professor S.N. Singh, our esteemed director, Dr. Padmavati ma'am, Associate Director, SSPL, DRDO, Delhi. She has been kind enough to accept our invitation and to be here with us. Professor Pankaj Srivastav, the Dean of Academic Affairs as well as Faculty Affairs, and also my colleague in Department of Engineering Sciences, Head of the Department of Engineering Sciences, Dr. Ajay Kumar, colleague of Department of Engineering Sciences here, Professor Janil Dhar, and other colleagues from different departments, various speakers from overseas as well as India, and of course the participant of CANDEE 2023. First of all, I'm sorry that we are starting 30 minutes late. So extremely sorry for that. But there were two back-to-back events, and so managing the show was a bit difficult. Anyway, so but we have started. So the idea was basically when we thought of organizing this conference. Actually, the journey started in 2009 when we started a conference on materials science and technology. It was a national conference in 2009, and there was participation from University of Manchester, Practicing Lerato, Pankaj knows very well that how we conceptualized that idea, and we started this journey of organizing the conference in Department of at that time it was not Department of Engineering Sciences. In fact, last only esteemed director Professor Singh has categorized us as a different department, different streams working together. And earlier it was the whole institute and people are from different specializations they are working. And in the same year, in 2008, actually, we formed Advanced Materials Research Group. So it's a journey of almost the 15 years we have contributed so far as a computational modeling people working in different sectors, especially energy and environment. We started our journey with metric modeling using few open source tools. I remember that Siesta and other Avenue tool we started our journey with. And I'm a guy with peer potential. So I started my journey with the pair potential, and then we shifted to a few licensed tools, and currently we are more focused towards the tool like Vienna Atomic Simulation Package VAST, and the tools like the Atomic Toolkit Virtual Nanolab ATK VNL. Along with that, for computational chemistry, we are using the tool called Nanomaterials. So there are many tools, thanks to the administration of institute and various funding agencies who have supported us in establishing a very nice lab in this campus. And we have more than 30, the nodes available in the laboratory, and 3 servers, heavy-duty servers are there, and 4 logins on the CDEC machines, supercomputers. And of course, now we have the access of working in different laboratories like Michigan Tech and in Clemson University as well. So in this journey so far, that as I said that we started our journey with the LCMAT conference 12/9, and then we thought of organizing few workshops for the young people, the um, people who are in the physics and chemistry and material science and nanotechnology basically domain, this domain. And we organize this workshop for training these people basically in these tools. We wanted to be in the central India, the give a best repository of the tools in terms of the material modeling as well as device modeling tool. And of course, we can proudly say that we have achieved that target, and we are helping many institutions in Madhya Pradesh as well as outside Madhya Pradesh. Their students are coming, their faculties are visiting the lab, and they are utilizing the facilities we have in the campus. And so for coming to this conference basically, so I remember that when we joined this conference, and Dr. Vinod Sharma ji is here. So Dr. Vinod Sharma is from energy sector basically. He's from Italy, and Professor Hassan Singh, our director, he connected me with Dr. Vinod Sharma ji. So we contacted, and it was a very sketchy idea in the beginning, and we conceptualized, and we are thankful that Dr. Vinod Sharma, along with his colleague in ENA, so they have accepted to be the partner of this program. And later on, Nepal Physical Society, they have also accepted to be partner of this. And then, we approached few funding agencies because without funding agencies, it was difficult to organize the conference. And this is completely self-sustained mode, this conference. So thanks to the funding agency, CSIR, SCRB, and MapCost and DRDO. So everyone has supported me to organize this conference. So in this conference, we have received tremendous response by the participants as well as speakers. And most of the speakers are my friend. So thanks to all of them who have accepted a very short notice, because we launched this event in September only. Normally, international conferences are announced 1 year before, correct? Actually, but we announced in September, just three months before, and luckily, more than 40 speakers they have accepted our invitation, and we are going to be here. Only the dropout is 15%, so it's a very small dropout. So out of this 44 speakers, you'll be witnessing in these 2 days, basically in physical mode as well as in virtual mode. 21 speakers are from overseas, and more than 100, the abstracts we have selected for this conference. We have received 184 total abstracts, and out of 184, we have selected 106 or 107. And divided into various categories like oral presentations, poster presentation, some thesis presentation, even scientist presentation, like that, we divided all them. And some of the oral presentations were so good, we converted them into short and write down. So that was not the plan earlier, but we did this because of the quality of the work and the credentials of those contributors. So few talks are basically short and write talks. And along with that, we thought of because the concept is not basically because we are just is ending today another conference we started yesterday. Atal Research Incubation Conclave. And the idea was how to translate the lab research into a market-ready products. And so the concept was basically coming lab to market and especially focusing on nanotechnology domain. And we would find out three entrepreneurs, three startups. Uh, uh, we thought of felicitating them for their contributions in nanotechnology domain especially. So Dr. Sandeep was supposed to be not available today, so we felicitated him yesterday, and Mr. Akshat Shah from Hexor, so he'll be connected online, and Dr. Manju Vilash Shelke will also be online, so we'll be felicitating them. So both are startups. One is from NCL Pune, and that's from Hexor. In this program, there will be total 19 sessions in physical as well as in virtual mode, and I hope that these 2 days will be deliberating on various issues. The topics have already been given, and tracks have already been decided. But the main focus theme is all that, as the title of the conference says, that we are more interested in looking at what are the various advances in especially in the nanomaterials and nanomaterial based devices, and specifically focusing on two sectors which are very relevant and very important these days, at national level as well as at international level, energy and environment. So let's see that how these 2 days goes, and I congratulate all of you for joining us, and thank you one and all sitting here and accepting our invitation to be with us. And let's see these 2 days. I'm pretty sure that going to be very fruitful. Thank you so much.
We would like to invite Dr. Ajay Kumar Sir, Head of Engineering Science Department, to address the gathering.
Good morning to all of you. Respected dignitaries on the dais, participants, speakers. Uh, I would say that I welcome you all from the Department of Engineering Sciences. On behalf of Engineering Sciences, I welcome you all. Let me first tell you a brief introduction of the department. The department was established last year in July 2022, and at that time the name of the department was Department of Applied Sciences. Later it was renamed this year, and it is renamed as Department of Engineering Sciences. At present, the department has 9 faculties, out of which 2 faculties are from physics background and rest of them are from mathematics background. This is the second international conference in this series, CANDEE, and this time the theme of the conference is pure water and green energy. And I wish that this conference will be a successful event. Thank you. Thank you very much.
We request all the dignitaries to unveil the abstract booklet of CANDEE 2023.
Yes. Sir.
Moving on further, we have felicitation ceremony for Dr. MBG Padmavati Ma'am, Associate Director, SSPL Delhi. Congratulations, ma'am.
let me read the citation of Dr. Padmavati ma'am. So Dr. Padmavati is a renowned scientist in the domain of semiconductor materials and characterization. She obtained her master's in physics from IIT Madras in 1985 and MTech in physics in 1988 from IIC Bangalore. She joined Defense Research and Development Organization as a scientist B in 1988. She is presently working as a scientist H and Associate Director in Materials and Solid State Physics Laboratory of DRDO. She is also the Technology Director at Advanced Material and Group Director at Material Management. Her special area of specialization include the epitaxial growth of C5 heterostructure using metal organic chemical vapor deposition, development of thermoelectric materials and devices. She worked as a project director for the development of thermoelectric material and cooling device technologies leading to the limited series production with an industry partner. Co-project director for the development of nitride-based material structures using NOCVD for different projects leading to development of device-grade material structure for technology development. She has more than the 50 cited publication, international journal and conference of review, and has one patent awarded to her. And she has been instrumental in various activities related to the defense research. And some of the research cannot be disclosed, and then of course some of the research are in domain. And of course, she has a lot of contribution towards the nation, especially in the technology domain. And she has received a number of awards, Tiradio National Science Day Coalition Medal in 2006, and Associate Technology Group Award for 2018 as well as 2020. So I congratulate you, ma'am, for your contributions in the field of science and technology, especially in the defense. And as a physicist, uh, I really appreciate the contribution you have made. So on behalf of CANDEE 2023, we would like to felicitate you. People sitting on the stage, all are very renowned people, contributed in different sectors. And in series, Professor Ravi Pandey is here. Professor Ravi Pandey is noted an extremely exemplary researcher and academician in the domain of computational materials physics. He obtained the bachelor's degree and master's degree in physics from Dr. Hari Singh Gaur, University Sagar. So he's from Madhya Pradesh. We feel honored, sir, you to be here with us. And he did his doctoral degree in theoretical solid state physics from the University of Manitoba, Canada in 1988. He is presently working as a professor in the Department of Physics at Michigan Technological University, USA, and also serving as the Dean of College of Sciences and Arts at Michigan Technological University, USA. Engaging in multidisciplinary endeavors, both theoretical and experimental, he has contributed significantly to the development of programs focused on crystals, surfaces, and nanostructures. Some of his highly cited research involves bulk alkaline earth sulfides and gallium 203, low-dimensional materials, for example, graphene, boronitride monolayer, phosphorine, and antimony, and their heterostructures, transition metal banking complexes, and bioconjugated nanomaterial. So he's more in nanobio domain currently. I'm really lucky that I'm part of his group. He published more than 450 research articles in various journals and conferences with a whopping of 14,000 citations and a remarkable H-index of 62. He's also a fellow of American Physical Society. Sir, we are pleased to have you here with us and to felicitate you on behalf of CANDEE 2023. there was supposed to be another speaker and keynote speaker joining this program, but due to an urgent meeting in ministry, he couldn't join. Let me just read out his citation as well. Professor Rajiv Ahuja. So, Professor Rajiv Ahuja was born on 15 July 1965. He is a noted and exemplary figure in the domain of solid state physics. And luckily, he has also been my mentor. I did my postdoc with Professor Rajiv. Presently serving as a director and professor of IIT Roper and officiating director of IIT Guwahati. He graduated with master's degree in physics in 1986 and doctoral degree in solid state physics from IIT Roorkee in 1991. He worked as a postdoctoral fellow from 1992 to 1995 at Uppsala University, Sweden, where he joined as assistant professor in 1996 and promoted to a position of associate professor in 2001 and professor in 2007. He is also an adjunct professor at Florida International University, USA, and associate at Physics Department of Harvard University, USA, from 2004 to 2005, special senior researcher at Swedish Research Council from 2003 to 2009, and he has received several awards and recognitions such as Fellow of Royal Society of Chemistry in 2021, elected Fellow of American Physical Society in 2019, cited elected member of Congrelia Veterans Club, Associate Sweden in 2011, elected member of the Board of European High Pressure Physics Group for 13 years, and Royal Swedish Academy of Sciences has also awarded him and many awards on his name. In 2017 at Oral USA, he has received APS March Award and the Global Initiative of Academic Network by MHRD in 2016 and 18, and other awards like a scheme for promotion of academic research collaboration by MHRD in 2019, and more than 30 postdoctoral fellows he has supervised and 33 doctoral scholars and published around 1,000 research articles in international journal of the group, including 6 in Nature and number of papers in Sciences and PNAs, among others. And especially in the area of energy and environment sciences, with a whopping of 34,000 citations, an outstanding H index of 86. He has a one patent on his spintronic on his name, and more than 100 talks he has given. So we congratulate you, sir, though you are not available here. So I'm just reading out the citation. He'll be deleting his talk here that he could be his talk tomorrow morning online. So I have one more person sitting here, and I have not disclosed anyone, in fact, to Sir, who has contributed a lot in the power sector, energy sector, Professor SLC, our esteemed director. So let me read out this title. Professor Srinivas Singh obtained his master's degree in 1989 and doctoral degree in 1995 in electrical engineering from IIT Kanpur. After working as assistant professor at the University of Roorkee from 1996 to 2000, and Asian Institute of Technology, Thailand from 2001 to 2002, he joined IIT Kanpur as associate professor in 2002. Then he is a professor at HEG since 2014, and Professor Singh also worked as a Humboldt Research Fellow at University of Duisburg, Essen, Germany, and visiting professor at Denmark Technical University for about a year. He has been a vice chancellor for Madan Mohan Malviya University of Technology, Gorakhpur from April 2017 to July 2020, and presently he's director here at in Gwalior. He has received several awards, including Young Engineer Award 2000 of Indian National Academy of Engineering, Khosla Research Award of IIT Roorkee, and Young Engineer Award of CBIP New Delhi 1996. Professor Singh is recipient of Humboldt Fellow of Germany and Otto One State Fellowship of Denmark. Singh became first Asian to receive 2013 IEEE Educational Activity Board Meritorious Achievement Award for continuing education. He is also recipient of INAE Outstanding Teacher Award 2016 and IEEE R10 Region Asia Pacific Outstanding Volunteer Award 2016. And he is appointed as IEEE Distinguished Lecturer of Power and Energy Society from 2019 and Industry Application Society for 2019 to 2021. He is also a recipient of NPSC 2020 Academic Excellence Award and 2021 IEEE Industry Application Society Outstanding Educator and Mentor Award. His research interests include the power system, restructuring flexible alternating current transmission systems, power system optimization and control, security analysis, wind power, etc. And he has published more than 550 papers with agendas of 16 and more than 14,000 citations in international and national journals and conferences, and supervised 41 PhD so far, and he has also written 31 books, 2 chapters and 8 edited books, 2 textbooks, and he's completed 3 dozen of technical projects in India and abroad, and his 2 NPTEL video lectures everybody can see on HVDC transmission and power system operation and control are well appreciated by the community. So Singh has been chairman of IEEE UP section for 2013 and 14 and IEEE R10 conference and technical seminar coordinator, and also R10 vice chair at technical activities. Dr. Singh is a fellow of IEEE USA, IIT UK, INE, EAI, and IETE. And with this, we sincerely thank Professor Singh for his contribution to the scientific community, especially in the energy sector. And thank you, sir, for joining us and guiding us. We would like to, on behalf of CANDEE, to felicitate you.
We would request Dr. Srinivas Singh sir, Director of ABB Triple IGEN, to please come upon and address the gallery.
Good morning to all of you. People sitting on the dais, off the dais, my faculty colleagues, dear students, participants, ladies and gentlemen. This conference, no doubt, Professor Anurag also told that we started slightly late, but always if you are delivering in the proper way, the leads must be managed. You can start the program 2 years back, 3 years back, yeah, even have a Panchvarsha Yojana. And if it is not coming in the flows, no use. So the delivery is more important. The days of today, where the technology is very, very important. We basically started thinking that's my view that each department here they should organize some sort of FDPs, conferences, research conclaves, plus involve everybody on the floor at a different level because as you know, they are institutions. We are the teachers, researchers, students, so they should come on the same platform so that we can meet an expectation of any good academic institution. And this is one of them. Coming to INEA, who is also part of this, you know, Sarmaji, when I was the vice chancellor, he met me in the Gorakhpur. And then we had already that institute was having some MU with the INEA because they are very good in the all energy sectors. So I happened to be in Italy, and then I told to him I am coming there for some other purpose. So I visited his facilities, and I found it's extremely very good. And after that, I left Gorakhpur. And fortunately, I was traveling from here in Gatiman and going to Delhi. He was in front of me. So we both were thinking, we have seen somewhere each other. So I was also hesitating. I have seen this person. He was also hesitating. So he just said, "Are you SNC?" I said, "Yes." Then I realized, oh, it's because Sarma, you can see the first day after 3-4 years, we met in the train. And here, just going from Gwalior, he was coming from, I think, Bhopal and by the Gwalior and going to Delhi. Then we started again further connections, and then he said, why not we can do some more initiatives and the collaborative work with our institution. I said, yes, why not? Then I asked Anurag, because he's external relation also the dean. I said, why not we can do something associated with them, because they are very good in the energy and environment aspect. And the final, you can say that we are delivering. So thank you and welcome Sarmaji in this conference. Pandeyji, basically he's a friend of one of my gurus at IIT Kanpur. I did the PhD with Professor Kalva, and both were same doing the PhD in the Manitoba in Canada. So we are meeting after here, and this, you know, so whole world is a linkage each other, And you'll find this research community or the teacher community is very small. We can meet here and there, and finally, we should have some linkage and networking. These conferences are giving these opportunities, and that is a very, very important. No doubt what you have done, you are presenting in the 10, 15 minutes your work, and so few people are listening, few are not listening, and so finally you are also happy and others are also happy going back. So that is not a major attraction of any conferences. The conferences basically they should basically give something more than simply paper presentation. Nowadays, the networking is a very, very important, whether you are connected with the social media networking. Everyone is having, I think, WhatsApp, Instagram, Telegram, jitne bhi WeChat, everywhere we are here. So that is, you can say, that is not in person. Conferences provide the networking in person, and you can meet the friends, you can make the friends, and also you can help create the future networking that will certainly not maybe the today advantage, just maybe the future you will find that is very, very useful. In this conference, you can see many conferences you have seen, mostly dedicated one or two invited lecturers and simply having the 10 parallel sessions and presentations, and only there is 10 papers in that, and 10 people or 5 people are presenting, and finally that's everything is wrapped up and finally we conclude the conference. But in this here, the whole theme and the design is pretty different. We want in the oral presentation there will be some sort of the invited lectures, and these people are selected in such a way they are the stalwarts in their area. It is not maybe directly related to your area, but I'm sure, listen them, and try to correlate what you are doing, what they are doing, can be any common. Yeah, some portion will be utilized in your work. And that is always nowadays we see the multidisciplinary results. So in each sessions, it is they planned for the 2 hours presentations, and some invited keynote speakers are there because we had the large number of papers we presented. That's why we kept in the parallel 2 sessions. But always I think this invited talk should be the combined one, so that one people should not miss and he should not say whether he should go in this room or that room. So, but due to the limitations, the time and other you can say your valuable time as well. So it is the 2 rooms, but they are very close. These 2 rooms are there. So whenever you found any interest, try to walk in that room and try to listen to those speakers, because they have basically they are if with the, what they are speaking in 1 hour or maybe 30 minutes is a complete a book. So they are the encyclopedias, and they are having all the information which you will require a lot of time to read. May not sometimes find those things you can listen and you can interact with them. So there is also a lot of interaction times are there. A lot of there's lunch, dinners, breakfast, tea. This you can also interact in that period. And also the evening today, I think they have organized some after the tiring presentation and discussion, some light entertainment music and other programs. And also, I guess I think I saw this. There or not, I'm sure it will be here. And then of course there will be some gala dinners also there. So you just try to interact. Try to, no doubt you are presenting your work, no doubt, but try to listen to the speaker. Always I insist, because once we are the researchers, very difficult to listen others, because we say, oh, it is not useful to me. But not today. If you have those terminology, those things, not today, I'm sure that tomorrow it will be very, very important. You see this our institution. It was conceived and the concept that those times by really thank the politicians 25 years before, they thought that the IT will be one day this the future of the nation or world. And you can say this IT is very fast. This institution was only the research, BTech plus MTech or BTech plus MBA. That was the conceived 25 years before, and you can see now it is everyone is talking about IT and computer science. So that's you can see now it is coming. So similarly here, the many people will be talking the different aspects. Some people will be talking hydrogen energy. Although it is very difficult for the using for the small purposes, but that can come and that safety security and the terms are solved properly, we can go ahead with it. So this everyone talks energy, everyone talks environment, but coming collectively, doing something together, that is one of the motto of this conference. So the many sponsors are there and they have supported. Thanks for them for supporting, and thanks for all the delegates visiting our campus. This is a lustrous green campus, and try to walk in the morning and evening. Certainly, you will have a very fresh air, and you will see a lot of peacocks and others, even though it is all around this campus. So it's a green campus. So I hope your stay will be comfortable, and you will be once you are going tomorrow after this World Conference is over, you should have a takeaway from here in terms of your knowledge, in terms of your connection, in terms of your networking, whatever, and that will be useful for you. So I wish this conference a great success. Thank you very much.
Now, we would like to invite Professor S.L. Chaplet sir to please come forward and say a few words on the auspicious occasion of inaugural ceremony of CANDEE 2023.
Thank you, Anurag, for inviting me, and let me add my word of welcome to all of you. I am really impressed by the excellent felicitations that you presented, and I don't have to repeat it, but I would like to really wish this conference very well. What I should say, I mean, yes, I think that this IT management, then nanotechnology, and so on. Now we are talking of quantum technologies. So I'm sure you have introduced already some courses on that, and probably are there any talks on quantum technologies related? Yeah, but I'm sure this particular CANDEE workshop will conference will continue in future, and I'm sure that is the kind of things that we will look forward to. So, in fact, this technology is not simply developing; it's exploding. And as I think Professor Singh said, the networking is something that is extremely important to be able to contain this explosion and to make sense out of it. In fact, we have this concept of parallel computers. Earlier, we used to have single computers, one processors. But then very soon people realize that networking and parallel computing is something that enables us to proceed. So, but we have kind of, with the conventional technology, with the 2 nanometer kind of transistors, reaching a kind of limit there. And of course, the future will hold for us. Another important thing I would just like to point out is about the tools, variety of tools that exist today, and well, I'm sure that all of them are getting upgraded, developed, depending on. This depends on the level of computational power you have at your command. So, I mean, you always make approximations or shortcuts depending on the computational power available, and that gives a certain accuracies. But this keeps going up. So we, as Anurag said, we started with very simple materials, pair potentials, then the density functional theory and these tools came up, which again had to involve a lot of computation, a lot of approximations, and as I think Professor Pandey would tell you that these developments have gone on and on to a much more sophisticated level, and instead from very simple structures, now it also extremely complex structures. For example, the high temperature superconductors, we are still not able to really predict or understand it fully well. So, in fact, the challenges are enormous, and I'm sure my younger colleagues will have a lot of opportunities to make progress, make new predictions, give new technologies, and the way we are going probably under 10, 15 years, we will have a different world. So with all the best wishes, let me thank you again, and thank you for this invitation. Thank you.
Thank you, sir. We would like to invite Dr. MVG Padmavati, Associate Director, SSPL Delhi, to please come upon and address the gathering.
Esteemed dignitaries on the dais and colleagues and my dear friends, I'm extremely thankful to the organizers for having invited me here. And as a representative of DRDO, the theme of the conference is very important to us. Though I come from a lab which primarily works on semiconductors, we don't have a direct connection. I mean, we don't work on these topics, but being a semiconductor lab, it is very energy intensive. And of course, the semiconductor processing itself has a lot of impact on the environment. So in that sense, there is a connection. And currently, DRDO is strongly looking at interactions with academia. And if you look at our webpage, you can see a lot of programs running. We are opening centers where defense, industry, and academia are interacting, and on various topics of interest to defense. And there is a strong thrust to boost the ecosystem for students to come up and work in the areas of interest, futuristic, new, current areas of interest for defense. So I would invite you all to look at our webpage and look at the various ways in which you can contribute to the defense ecosystem of our country. So I hope that some of the techniques and the materials you work on, you can uh, tailor that to whatever the needs of defense ecosystem of the country. And then I think that whatever discussions you have in this would definitely be exciting and contribute a lot to the country's, forward-looking way. So thank you very much, and I wish the current conference all the very best. Thank you.
Thank you so much, ma'am. It is now time for the keynote address, a moment that promises to set the tone for the conference. Our keynote speaker is a visionary in their field, renowned for their groundbreaking research and profound insights. Please join us in welcoming Professor Ravindra Pandey, Dean of College of Science, MTU, USA. Welcome, sir.
So let's start. Thanks, Anurag. It's really good to be back in Gwalior. I think his Michigan Tech has been coming to Anurag's workshop from day one. And we have a new member of Michigan Tech fraternity, Dr. Mandal is here. So hopefully it's going to be continuing. And this is again, as you know, I'm from Sagar and it's good to be in Gwalior for famous Gajak. And I still remember the first time when I was a student, I used to come for Tansen and music festival. So it's a fond memories. But the other thing is most important, I think I get to see my junior colleagues, Dr. Chakravarti, Dr. Pengre, and Dr. Sarkar. So it's good to be back. He used to call in the Gwalior gang. So thanks again. So let me start. I'll try to give you about 30-35 minutes about the physics And what will come on is Dr. Chibute said about quantum technology. We call it quantum materials. So give an idea, and since this is a triple ITM, the talk is going to be more sort of applied aspect. I'll pick a few examples and give you that we have to have a ground reality before we do a modeling of materials. So I'm at Michigan Tech. Michigan Tech, as some of you know, as I've been there, and Rag was there, is really close to Lake Superior. I think LED is not going to come. So I'll use my hands, this thing. And then, although we are in Michigan, but we are far away from Detroit, but it's a beautiful town, reminds me of Sagar, hilly area with a nice canal. So in my group, as Anurag said, I've been moving from starting with the crystals, clusters, nanostructures, 3D materials, and so-called nanobio world. But in this talk, I'll more really talk about quantum materials or semiconducting monolayers. What we are trying to do is establish a structure property relationship. And the whole idea is what we'd like to convey, that we have to have a fundamental understanding and theoretical foundations of interactions. That's the key thing, interactions. And once we have the understanding, we can always go and look at the electronic, optical, or mechanical response of the materials. So that sort of goes in and out and hand to hand. So we talk about the low-dimensional materials, which we call quantum materials. And again, we have to be thankful to experimentalists. Because of them, we could really look into surface topography at atomic level. And one of the examples is, which can show you either atomic force microscope, which gives you high contrast, look at the physical properties, or a scanning electron microscope, basically gives a high depth of field, so you really can look into the chemical composition. And here one of the examples is really to pinpoint a nanometer size gold clusters using one of the techniques, in this case is the air. I like this slide because you can see here sort of progresses very well as we move forward. If you remember the graphite pencil is a normal original size, you zoom in using optical microscope, you can see sort of the structure or topology of the head. Once you move forward to electron microscope, which is about 80,000 times, you can leave really nice sort of structures. But if you go further down, about 30 million times, the STM, and you can see really a sort of a hexagonal ring forming the graphene sheet, which is a part of the graphite. So this is why I like about it, because it connects both experiment and theory. Can you hear me without a microphone? I want to do the hands. So if you go from left to right, we talk about optical microscopy, and you can see connect is sort of the modeling aspect of this thing. So what we have is a continuum theory, and as you go down, so you are basically looking at the time scale on y-axis, and on the axis you have length scale. You further come down, what we're talking about the high resolution transmission electron microscope, we're really pinpointing the atoms, and what we have the tools of quantum mechanics, we can describe the sort of these interactions, the atoms in a given material. So now we talk about the interface. So we have the tools. We can look into what is going on in the material or in the devices. On the left hand side, we have a heterostructure, it's gallium nitride / graphene. And you can really see is basically the top is graphene bilayer, and then you have the gallium nitride monolayer, and then you have the substrate. So you can really image what is exactly in the atomic details of that interface. On the right hand side, we have the rounding tools of quantum mechanics. So here you can see here we have a carbon nanotube, And as you know, carbon nanotube has sigma and pi bonds, which are interacting with one of the DNA nuclei, the guanine. Really, can you map out the electron density or the interaction between a molecule and carbon nanotube, which you call is a van der Waals type, the weak interaction. You can really see. So this gives you sort of the limits of what we have really advanced, both imaging and sort of a modeling perspective. So what I would like to point out, giving a couple of examples is what is the role of interface? Because we have the material, we take the material, we form the device. Device means you have to have a contact. It's the source drain, and you have the gate field. So how does this interface with quantum material sort of interact and sort of dictates the physics and chemistry of this coupled system? So I'll pick up the first example is a graphene-based reactor structure. We're looking at the electronic properties, especially the field effect transistors. Then I'll switch the gear and go from electronic to mechanical properties. And if you have time, I'll look into some of the optical properties. It's defined by these interfaces. And mainly we use the DFT, the CSTA, WASP, Quantum Espresso, our Gaussian program packages, the standard either GGA or van der Waals interaction in the exchange and cohesion form. So let me show you one cartoon is this is a CNT based device. Of course, CNT is a semiconductor. What you can see is indeed we have the source and drain gold contact, the gate arm is gold, substrate is silicon dioxide, and a single carbon nanotube can act as a rectifier. And you have the so-called the terms where you have the current versus voltage, and the gate voltage, by varying the gate voltage, you can manipulate the current. So what we can do is we can really make these free effect transistors using a single strand of carbon nanotubes. Now comes the graphene. As you know, graphene is the advantage of the graphene is because of being a zero gap material, it's very high electron mobility. So that really gives us a very good sort of material to look into it. But there is a problem. The problem is graphene is, as you know, at some of the high symmetry points, the valence and conduction band, the like each other. So there is a zero gap. So the whole idea came out almost 10 years ago, how to induce a band gap in graphene. So you have to start with the hypothesis. So what we know is in a graphene sheet, a band gap opens up only if the electronic density of these two carbon atoms, they are inhomogeneous. So the efforts have been made is, let's make a graphene bilayer, apply the electric field. So what happens is this bottom layer and upper layer, they experience a different electric field, and they induce a inhomogeneity in the electronic distribution in the graphene layer. We talk to experimentalists, they say, yeah, this one can do it, but it's not easy to make a device because you have applied electric field as well as the gate field. So idea came through in our group is let's use one of the monolayers to form a structure. We realize graphene and boron nitride are structurally similar, but graphene is zero gap material, boron nitride is semiconducting with a gap of 3 or 4 electron volts. So our idea is if you bring in these two monolayers, structurally they are same, electronically they are different. So you do all these calculations, you form the equilibrium configuration, and then you look into the band gap. See what happens to the band gap. So you can see here we have graphene, then we have boron nitride bilayer, and then heterostructure, which you would like to see. So for the students, always when we do like in modeling, you have to have a reference case to see how good or how so not good your modeling or predictions are. So for this case, we have picked up the boron nitride bilayer. Boron nitride is semiconducting. You can see a gap at K point. Boron nitride bilayer, more or less same. You have a larger number of bands because there are two monolayers. With the graphene, and again K point, you have the Dirac cones or the zero gap. And if you have heterostructure, more or less it looks like a graphene, but if you zoom in, but you can see there is an opening of the gap. So whatever we started with the hypothesis is once we have this graphene and boron nitride monolayer, because of the one carbon atom sees boron, the other carbon atom sees the nitrogen. Because the interaction, the inhomogeneity in the carbon sublattice, which sort of opens up the gap. So if this is true, then you have to do computer experiments. Computer experiments to prove it. So our idea is we start with the equivalent configuration and let's reduce the configuration, the interlayer separation. In a sense, you are increasing the overlap between graphene electronic density and boron nitride monolayer. So if this is the case, then what you see, as you reduce it or you apply the strain, the band gap should open more. So in the x-axis you have the strain, and the y-axis you have band gap change. You can see the band gap opens up because of this interaction between graphene and boron nitride monolayer. So far so good. So idea came out is let's use this graphene boron nitride bilayer in a device configuration. But before you do it, let's look into the constituent graphene or boron monolayer when you form a device. So here one of the cartoons you have is the gold context, left and right, and then you have a channel material, which you can see in the black is the graphene monolayer. So we form this device configuration. We use so-called the non-equilibrium Green's function approach. We sort of take the quantum scattering part, and then we have the semi-classical, the electrodes. So it takes care of the self-consistent field wave because, as you know, the quantum region is embedded in the semi-classical region. So what happens is this electronic density tends to bleed out in the electrodes. So that's why we have a larger number of sort of monolayers of gold compared to graphene monolayer to make sure the electronic density is contained in that region.
Hello.
You have it. Then let's look at the current versus voltage characteristics. As you know, graphene is zero gap material, so you have current versus voltage. Graphene behaves like the ohmic conduction. You apply the more voltage, you're going to more current. Surprisingly, what we found here is boron nitride. Although boron nitride is semiconducting, the gap of 3 electron volt, it does behave like a ohmic conductor. So when the student showed me this result, I said, go back and do more calculations. After 3 months, he comes back again. Same answer. Then we thought, let's look at it. What is going on? So we sort of zoomed in and look at the interface. So as you know, is a gold carbon bond is pretty strong, forms a nice bond. So you have, if you look at the left hand side, is at the interface, is the electronic overlap between gold and then carbon atoms. Surprisingly, if you look at the boron nitride, so I came to know is the boron is an electron hungry element. It loves electrons. And as you know, gold has a lot of electrons. So it turns out to be the gold boron bonding is much stronger than gold carbon bond. So in this sense, this interface bonding has provided the additional conduction channels. And that's why boron nitride monolayer behaves like a graphene, although it is semiconductor. That's good. But then I told the student, you have to prove it. If this hypothesis is correct. So what you do is, in computer experiments, you try to weaken the interface effects. So our idea is, this is our equilibrium configuration. Let's increase the distance between contact and graphene monolayer. That's going to be weakening the interface effect, and graphene boron nitride then should show a distinct characteristics, IV characteristics. In this case, you can see here is what we are doing here is that you have the numbers 3.1 angstrom, 3.4, 4 angstrom. This is, we are moving away from the monolayer and the content. You can see the transmission, which is again a major IV characteristics. Sort of it goes down, but at 0, which is our first sort of energy, still we have the channels. So that's good, because graphene is a zero gap material. You've got to have the channels to have the conductivity. Let's look at the boron nitride. And interestingly, what you expect is, as we are weakening the effect, boron nitride should behave like a semiconductor. You can see at 0, 3.1 angstrom has a finite transmission, 3.4 is a little less, but 4 angstrom away, there is hardly any transmission channel. So boron nitride behaves like a semiconductor. That's the one way of proving it. The second way of, when we talk to experimentalists, they would like to have not a monolayer but a thick layer sample. That's easier to handle. And Jesse can tell you, the monolayer we talk about, forget about it. So I thought is what we do is, let's look at what happens as we go graphene, monolayer, bilayer, trilayer, boron nitride, monolayer, bilayer, trilayer. See what happens to IV characteristics or conduction. In the left, you can see the black is monolayer, then we have the orange is a bilayer, and the green is trilayer. So at 0, which is a Fermi, the top of the valence band, you can see there's a finite transmission channels are there for graphene. So although graphene goes from monolayer to trilayer, the transmission reduces, but it's still there. With the boron nitride, the monolayer is a black, it's a very, very large transmission. Bilayer is a red, it goes down. But for the trilayer case, it really becomes a semiconductor. So what it comes down to is if you use a boron nitride monolayer as a single monolayer, single layer, the interface effects are going to be dominant, no matter what the materials characteristic is. And the key thing is the multi-layer boron nitride can only act as a direct. So when we talk to experimentalists in our university, Dr. Yad, he looked into the conduction, the characteristics. And you can see here is the monolayer boron nitride, all this is a band gap. It still shows sort of a little bit of ohmic conduction. But when it goes from monolayer to 7-layer boron nitride, indeed you can see here is a diode-like state, which tells you if whatever the prediction came out from modeling is correct. So the message to young students and then postdocs is we talk about low-dimensional materials, but the question is you have to think about the interface effects at label, because we are really talking about nanoscale in that sense. And when you go from material to a device perspective, you have to have a multi-layer system, because it's not easy to handle a monolayer system. We change the gear. Let's talk about the mechanical properties now. Is what kind of information we can sort of receive or obtain using these so-called the first principles methods. So it's a total different extreme now. We are talking about the macro one now. So we received a funding from NASA, and what they talk about is you have to design so-called the carbon nanotube based the composites. What they call a deep space exploration, because what expectation is going to be a light material, but much more stronger. But again, using the tools of modeling. That's okay. One of the students who joined my group, Geeta, I said, let's look at what is the composite is. Because coming from solid state background, you don't have much about the composites. So she showed me this thing is polymer composite is nothing but a polymer matrix. then you have a carbon nanotube or any low dimensional material working as a fiber. The expectation is this fiber, the matrix, the interface basically takes the burden or the load of the material, and that's why the material is a little stronger than matrix itself. Some of the definitions is what they call is in terms of the stiffness, they define stiffness as the response, mechanical response. And when we have the so-called the weak interface between fiber and matrix, they say is basically is the material sort of resists the fracture. So it is much more durable compared to we have a stronger interface where simply it becomes a brittle in that sense. So this is the way they make composites. You start with a graphite, you mix with a sort of a so-called EG or from the chemical polymer matrix, epoxy resin. You mix everything, and then what you have is the composites. Now, how do they experiment this? So mechanical engineers, how do they test out how strong the material is? So this is a cartoon here. Is what they say is this called pull-out approach. It's a tensile, or what you have is sort of a shear approach. It's in plane or out of plane in this sense. So our idea is let's look at the so-called the tensile strain to apply to the material and see how good the material, and we can guide the experiment. Because the challenges you're looking at it, you have the composites, you have the processes, manufacturing processes, which involves the heating, and then you have the design factors. So we have in a sense 10 fiber options, about 30 plus matrix options, and of course then you add manufacturing options. So our plan is can our simulation or can our predictive value sort of guide experimentalists to look at this vast space to only few samples to work on. So you start as you know, we started a thesis. So Geeta started let's make a workflow what we would like to do. So you have so-called the monomers, which I'll show you a lot of monomers. Again, it's the organic molecules, a lot of atoms, basically carbon, hydrogen, nitrogen, and oxygen. You combine this with graphene or boron nitride or CNT, whatever you would like to do. You apply the periodic boundary conditions in our periodic supercell, and then you optimize to obtain the ground state equilibrium configuration. And this is again the DFT approach. This is the van der Waals corrected functional form with a large cutoff to look at what is the total energy minimum for equilibrium configuration. So just to give an idea, this whole workflow with the different monomers takes about a year and a half. So it's not an easy calculation, but series of a lot of calculations. So this is so-called our the supercell, periodic supercell. Now the key thing, the problem comes in, and when you do these calculations, is what is the orientation of this organic molecule, monomer, on your substrate. So the ideal situation is you have the orientation, you give everything, and let the program optimize the whole thing. But this takes months and months. So you have what I call the guided bias optimization. The bias optimization, do you think about the orientation of the molecule is so-called the flip up, flip in, the vertical and in plane. And you sample the configuration space for optimization. Once you do it, you can calculate so-called the strength. And once you have the minimum or the maximum strength or minimum binding energy, you take this configuration as the most stable configuration. And as you expect here from is the interaction between monomer and the substrate is going to be the highest or the largest when we have the in-plane configuration. You can see the in-plane configuration, the right-hand side has the higher binding energy related to other configurations. So for monomer is fine, but again you dig into so-called polymer chemistry or composite chemistry. So a polymer consists of two components. a matrix which is a resin, and then you add so-called hardener to sort of solidify that polymer. So you pick up a different sort of molecules, epoxy, BMI, aerosol, then you have hardener, DPDA, or DVPA. So this all is the organic chemistry coming out, and you sort of sample both resin and hardener separately, and you see what kind of binding energy they're going to have. So what comes out is, this is good, but let's move to the simulation part. Okay. So we have all these 10 to 15 different monomers interacting with this thing. We got the binding energy with the equivalent configuration. But if you are to experimentally say, so what? Can you give me the numbers? How strong the material is? Okay, fundamental science is fine. So we said, okay, let's do it. So we talked to them and we said, how do you measure this mechanical response? They said this is called pull-out experiment. So they pull out the fiber of the matrix. So you can see you have the stress, and then you have the strain. Stress strain, which is typically mechanical response of the material. So as you pull out, you're applying the strain, it goes up because stress is higher, and at one point is the debonding. The fiber sort of comes out, and then basically complete pull out, we don't have any stress because these are two different materials. So we thought, okay, how can we simulate it? So we thought, okay, let's fix the substrate and simply pull out the monomer from equivalent configuration. So this is what we have is the energy versus distance curve. And we know the force is derivative of energy with distance, we can easily get the force. In this case, it's a one-dimensional case. Okay, otherwise, 2 or 3 dimensions is very easy, force over area, you can do it. So in the literature, we found is so-called the pseudo 1D equation state. So from there, we can really extract so-called the mechanical response terms from this energy versus displacement curve. You can see it on right. So you have the force, which is derivative of energy versus distance versus the strain. From this curve, what you can see is what you expect. Resins are going to have more or similar behavior compared to hardener. But there is a one hardener which stands out, which is in green. You can see here. It's called DTBA. It can sustain really a larger stress without being broken. So that's the one message from here. And if you look at it, this part is, so I told the student is you have to condense everything in one plot, visualization. And she came out with this plot, I said your PhD is done. You can see here what she has done is she's got a mechanical response, y-axis. If you look at the axis, the strain, and then you have the interaction strength. For the lower part, you can see is here is the resins or one of the hardeners. They call more or less same mechanical response. Just plus minus, 2 GPa. But as I said earlier, is DTGA really has a significantly higher response compared to other molecules. And then there are ways you can explain it because of the DTGA has this collateral rings and the overlap is stronger in this sense. That's good. But then again, my engineer friend said is you are doing one molecule on a substrate. That's not a polymer. You have to move one scale up. So okay, that's fine. So what we have done is we have the fundamental information about interactions from the quantum mechanical calculation. So we take those parameters and do so-called atomistic calculation. So instead of dealing with 100 of atoms, this is about 45,000 atoms. And what we do is we have to make a polymer. You can see the model polymer was done in the DFT or quantum mechanical simulation. Then we combine with the graphene of all these molecules. And what they say is you have to densify. So the experimenters believe in this polymer composite area called mass fraction. So you take in the mass fraction, we solidify this thing, densify it, then you combine, look at your graphene, or boron nitride, or CNT, whatever you have, graphene, and then what we call is to annealing and equilibration. And this atomistic, some of the parameters are you have, because we did about 100 picosecond at the 700K using NPT ensemble. And once you have it, then you move on and do the so-called equilibrium structure. That's good. Now we are going to simulate, because so we have a equilibrium configuration of 45,000 atoms derived from the MD simulation. Now, in order to see mechanical response, again we have to do the pull-out experiment. We have to pull apart. And what we do here, you can see is, in the one case is, we have taken up boron nitride for this pretty picture, is the epoxy boron nitride monolayer, and other case is the BMI. So we have two polymers, means is the mixture of resin and hardener combined with the nanostructure. You can see here, if I pull apart for epoxy BN for a given time, the strength is there, more or less remain intact. They don't break up. If I do the BMI, I can see there is a breakage. So in terms of physics, you asked why. So in terms of physics, there are two competing factors: intermolecular bond and intramolecular bond. In one case intra is stronger, and other case is inter is strong. And that's why the EMI and BMI and epoxy behave different. And if you look at the numbers, when you see stress versus strain, the epoxy, which is in red on the left hand side, you can see is intact. So at certain stage, it simply goes down. BMI takes time. You can see there's a smooth sort of curve coming down at a higher strain with a larger stress. So BMI can sustain the fracture related to epoxy. In terms of the numbers, if you look at the middle column of the toughness, epoxy toughness is about 1/3 of BMI. So message comes down to experimentalists is we can provide information. Yeah, this is last. And then the experiment, the guidance is, if you give it a choice of say BMI epoxy, we would like them to try out with epoxy, or rather BMI resin compared to epoxy. So I think this is the last slide. I have a little more optical, but I think I'll catch up with later, which we have done the so-called inaugural property. But in these two examples, I hope we have shown either electronically or mechanically, the first principle calculation can provide you really valuable information as long as you work with experimenters. On its own, the modeling does not have to make any value in a real world. You have to join hands to work together to sort of either explain the properties of the materials. So I have to move to the last slide, which I really would like to thank. Of course, you have to thank the gurus. I've been fortunate enough to have really a good role models and mentors. Then got to thank students, postdocs, and faculty colleagues, and especially Anurag. Thanks, Anurag, for inviting and having association as a student, as a postdoc, and now as a junior colleague. And thank you to all. Thanks.
Thank you so much, sir, for a fantastic talk, and introducing the lot of the 2D materials and the concept behind that, and how the molecules are interacting with the surfaces, and what is physics and chemistry behind that. And so let's thank the speaker, keynote speaker of this first session. And now we're moving towards the closing of this session, and all of you are invited for the high tea and a group photograph in the convention center, and rest of the the sessions will be conducted in the convention center locally. Okay, so let us move to the convention center. Thank you so much.